that males have higher risk disease than females, that older people get more disease than younger people, that high cholesterol is a risk factor, that high blood pressure is a risk factor. So before you even look at any of your analyses, in your analysis plan, you're saying, I'm probably going to have to control for age and sex and cholesterol and blood pressure. Now the question is, how do you control for those factors? So let's focus on blood pressure. How do you decide how you're going to represent blood pressure in your model? As I mentioned a few minutes ago, I would make the decision first based on prior knowledge. What do we know about the relationship between blood pressure and your risk of developing coronary heart disease? For what we know, see if I can draw something. This allow me to draw. Yeah. Oops. This might be what I might predict to be the relationship between a risk of developing heart disease if the risk was on the y-axis here. So if this y-axis is your risk of developing disease and your x-axis is your blood pressure. I know, other people have shown me that very, very low blood pressure, hypotension is bad. Your risk could be high. If you, oops, I don't want to draw lines anymore, so I'll leave the pointer where it is. Just use this little, I don't know if you see this little cross bar here. People with low blood pressure have higher risk than people with normal blood pressure. People with high blood pressure have higher risk than people with normal blood pressure. This particular curve might reflect, again, I'm about using that cursor, might reflect the anticipated relationship between blood pressure and your log odds of developing coronary heart disease. If so, let me erase this now. Erase this stuff now. To represent a J-shaped relationship, you do that by including a second-degree polynomial. Second-degree polynomial looks like an inverted U, or looks like a U, or looks like a roller coaster that's going up the hill, or it's going down a hill, or it's going up and then down. It has one hump to it, or one trough to it. So the reason I considered adding blood pressure squared to this model was based on prior knowledge. After fitting it, data supports that. Because after fitting it, notice the coefficient of blood pressure. The SBP2 term is p less than 0.05. The data is rejecting the null hypothesis that the coefficient of SBP2 is 0. If the coefficient of SBP2 were 0, B5, then the SBP2 term would drop out, and I would then have a straight line relationship. So really what I'm testing here is the significance of the B5 term. Null hypothesis is that B5 is 0. If the null hypothesis is true, I'm making a linear assumption. If the null hypothesis is not true, I'm making a quadratic assumption. Which two assumptions are best supported by the data? Well, the data gave me a small p-value. Small p-values reject the null hypothesis. They don't support the null hypothesis. The data supports my prior belief in a quadratic relationship. So model building is an art based on prior knowledge and based on data. It's a mixture of two. And the prior knowledge and the data in this case are very consistent with one another. Both of them suggest a quadratic relationship between blood pressure. I could add a cholesterol squared term to the model. See if that model fits better than the model I'm presently having, which is assuming a linear relationship. And that would help me decide between those two representations for cholesterol. The way you decide between two candidate models is by looking at something like the AIC statistic. The way you decide how to first consider representing a term in a model is based on prior knowledge. Based on what I know, I would expect a linear relationship between age might be reasonable. The older you are, the higher your risk. Cholesterol might also have that relationship. The higher your cholesterol, the higher your risk. But blood pressure is different. Wine consumption is another good example of something that might not be linear. We know that lots of alcohol is bad for you. But a little bit of wine with dinner tonight might be something good. The antioxidants, red wine, lack of antioxidants, whatever it is. A little bit of red wine now and then for a meal is probably going to lower your risk developing many chronic heart disease, many chronic conditions, including heart disease. So maybe if you're including wine consumption, number of drinks you have a week, a month, a year, it might be best to include that as a quadratic relationship rather than a linear relationship to show the benefit that a little bit of wine is better than no wine at all. A little bit of wine is better than lots of wine. So there are some risk factors that, based on prior knowledge, that might be expected to have non-linear relationships to outcome. Blood pressure is one of them. Wine consumption is another one. So tonight, have some wine. Patrick asked, but wouldn't adding something statistically significant make the square statistically significant as well? Wouldn't adding something statistically significant make it square significant? Well, I'm a little bit of a circular argument there, Patrick. I'm not sure what you're asking. If there really is a quadratic relationship, then this SBP2 term should have a small p-value. But if that quadratic relationship wasn't true, in other words, if I added the h squared term to this model and h squared wasn't necessary, my guess is h squared would no longer be needed. So, yes, I agree with what you're saying. By focusing on SBP2, we're getting an idea of whether adding SBP2 on top of SBP is important. We're asking whether adding a quadratic on top of a linear adds important information. In this case, for blood pressure, it does. I don't know if Aaron has the ability to turn on a microphone, because I'm not sure if I understand Patrick's question. I'm typing it in the chat box, might not explain it that well. So, Patrick, I'm going to have to just, you say, is SPP, if SPP is statistically significant, SPP is significant. No, that's not always true. In a model with both blood pressure and blood pressure squared, you might end up with the blood pressure term being non-significant, the blood pressure squared term being significant. It depends on the type of quadratic relationship. And here you should be just focusing on the SBP2 term. Okay, I'm going to stop now. Next week we're going to talk about continuous outcomes, linear regression. And hopefully we'll talk a little bit about Cox regression, survival analyses also. So I have time's up, so thanks everyone for joining me. Feel free to send me questions by emails. Maybe we can try turning microphones on next week if you have questions that are not easily answered by typing things in. But I wish you a great day. It's dark here in Boston. I'm going to start getting dinner ready, so have a good evening. And Aaron, why don't you hang on for a couple minutes, and then, but I'll let everybody get off right now. And Aaron, when you get a chance, when they finish logging people off or people log themselves off, you can turn on the mic.